In this video, we're going to look at some applications of our impulse-momentum relationship. Let's write that down just to remember what that looks like. We're going to have impulse being equal to force times time. We're going to have momentum being equal to mass times velocity. And so our change in momentum will be equal to our impulse, resulting in our mass times our change in velocity being equal to our force times time. And so we're going to apply that here first. We're going to have a car with a crumple zone and without a crumple zone running into a brick wall at 15 meters per second. And we're going to see how does that change the force that is experienced by the car, and thus the force experienced by the driver. So in the first one, we are without a crumple zone. And I've gone ahead and taken the liberty to figure out how much time it would take to fully collide and come to a stop with this brick wall if we had no crumple zone. So we're just saying that it's 1 centimeter. 1 centimeter crumple zone. Basically, it doesn't change at all. And then in the second part, we're going to look at with a crumple zone of 20 centimeters. I've gone ahead and calculated the time that it would take for both of those collisions to occur. So in this first case, I'm going to have my relationship between momentum and impulse. I'm going to have a mass times my change in velocity being equal to my force times time. And I'm looking for the force. Well, my mass is 1,200. My change in velocity, well, that's going to be my final velocity minus my initial velocity. Well, my initial velocity is 15, and my final velocity is 0. And so we're going to have negative 15. And then my force is unknown, and my time is 0.00133 seconds. And so if I go ahead and calculate that, I can divide both sides by 0.00133. That'll get rid of this, and I'll find my force. And if I do that calculation, then my force is going to be equal to 1.353 E7. That's 13 million newtons. That is a lot of force being experienced by that car. And it's going to be negative, which just means that it's going to be pointed in the opposite direction of the velocity. So my car is going to experience that much force shoving it to a stop when it hits that brick wall. Now let's try with a crumple zone. Now my mass and my velocity will be the same. But my time is different. So I divide both sides by that time. Getting rid of that, and I'll find my force. And there I get 6.742 E5. That's a negative again. That's going to be my force. So it's a full 100 times less. That's a lot. That is a significant difference. A lot of this force will get taken up by the car, and plenty of it will get transferred to the driver. So this difference by 100 times, just by including a larger crumple zone, is really going to play a pretty big factor in the survivability of a car crash. Let's look at another example. In this one, we're going to consider the idea of recoil. Now, if you've ever shot a gun, you know what recoil is. When you fire a gun, especially like a shotgun that has a lot of force behind that bullet, well, it's going to kick that gun back, and that's why we have to learn how to shoot it so we can hold it properly so that when it kicks back, we can hold it firm and it doesn't kick back and smash us in the face. So I want to figure out, first off, what's going to be the force occurring here. And then I want to figure out the velocity that this rifle is going to recoil at. So I've got a 0.7 meter long barrel, and I'm assuming that I'm going to accelerate uniformly throughout that barrel with a velocity on the outside edge of 325 meters per second. So what that means is I'm going to go from 0 to 325 meters per second in 0.7 meters. We need to figure out how long that's going to take. And to do that, we're going to use a supplemented equation. We're going to have x equals x naught plus v naught t plus 1/2 at squared. Now I don't know the acceleration, but what I'm looking for is the time. So I'm going to go ahead and use my acceleration equation, and I'm going to rearrange it to solve for acceleration. When I do that, I can plug that in for my acceleration. So I'm going to go ahead and first I'm going to take this x naught and move it to the other side and just say a change in x, because that's really all we care about here. Our frame of reference is just from the start of the barrel to the end of the barrel. So we're really only considering the difference in that distance. And then we're going to be equal to v naught t plus 1 over 2 times v minus v naught over t squared. Now, if I simplify that, this t cancels out this square, and I end up with, now this minus 1/2 v naught t takes out this guy, and so we end up with half of that remaining, 1/2 v naught t plus 1/2 v t equals my change in x. And we're assuming that the bullet wasn't moving when it was in the chamber. Before it was fired, it was motionless. And so this is going to be 0. And so I get delta x equals 1/2 vt. And so I can solve for t. I'm going to take 0.7 times 2, to get rid of that 1/2, divided by my final velocity, which was 325. And that'll give me my time. And so that time is going to be equal to 4e negative 3. 4.3e negative 3. And now I can take that back up here, and I can use that to solve for my force. My mass here is going to be the mass of the bullet, because I'm considering the change in momentum of the bullet. When I do that, I get my force being equal to 3,401 newtons. That's the force being applied to that bullet. Now, Newton's third law would say that the force that this rifle applies to that bullet is going to be equal to the force the bullet applies to the rifle. Let me adjust this. That rifle applies that force to the bullet, and the bullet applies that same force to the rifle. And so the rifle is also going to experience an acceleration backwards. Now, we could take this force and go force times mass equals acceleration. It's going to accelerate for the same amount of time that the bullet accelerated, and we could find the velocity that way. Or I could just keep in mind that my momentum at the beginning, my change in momentum total for both of these together has to be 0. My momentum is conserved. So my p total at the beginning will equal my p total at the end. What that means is, since both of these were motionless to start with, my momentum at the start was 0. So my initial momentum, say momentum naught, was 0. And so momentum now, after firing, has to also equal 0. So what that really means is the momentum of the rifle plus, let's say momentum of the rifle, plus the momentum of the bullet must equal 0. And so I can easily calculate the momentum of the bullet. That's just going to be v times m. And the momentum of the rifle is also going to be mv. And the only thing I'm missing is that v. So let's write this down here. Let's put it over here. So I'm going to have the mass of the rifle. It's going to be 9.5 times v plus the mass of the bullet, which is 0.045, times the velocity of the bullet, 325, being equal to 0. Let's calculate that. If I take my momentum and move it to the other side, then I'm going to have negative 14.625 being equal to 9.5 v. So I can divide both sides by 9.5, and I'll have the velocity of my rifle. So when I figure that out, my velocity is negative 1.5 meters per second. Now that should make sense. It should be a negative because the rifle is going to be moving in the opposite direction of the bullet. So there we go. There's our first momentum problem. And so we can see these relationships between momentum and impulse. And so now let's just do one more that's fairly simplistic. I've got a box moving at 25 meters per second. It has a mass of 5m, and then it has a ball of mass m thrown into it. So this mass is going to go into that box. What's going to happen to the velocity of that box afterwards? Well, the momentum of the box at the start has to equal its momentum at the end, even though it's got more mass. And so at the start, it's going to be 5m times 25. And at the end, it's going to be 5m plus m, the new total mass, times v. We want to solve for v. Now, both of these have m in it. I'm just going to cancel those out, and we're going to end up with 6m. So we're going to have 5 times 25 equals 6v. I divide both sides by 6, and I get 5 times 25 divided by 6. And I end up with a final velocity of 20.8 meters per second. So once we're able to apply these concepts of momentum, they're actually going to make a lot of these changes in motion problems a lot simpler. We're able to do things that we've never been able to do before, or at least not simply. So now that we have an understanding of all of these dynamics, all of these forces, all of these kinematics, we're able to apply them in new and diverse ways to tackle some really challenging, complex situations and solve them pretty simply.